So this is lecture number 7 of this course, and we are going to do something a little bit different from what we have been doing until now. Until now, we have been talking about what I would call as-is process analysis. We analyze the process as it currently is. That's why we call it as-is. So we take data about the process, for example, last month's worth of data, or the last 3 months worth of data, and we try to discover a process model out of it, and look at the performance statistics on top of that model, or we go and look at dashboards to compare different subsets of the process during the past 3 months. So it's all historical analysis, it's all about analyzing what has happened, or at most, what is currently happening. Now I'm going to introduce you a technique that allows us to reason more about hypothetical future scenarios. And this is important because in practice, once I have identified that there are some issues in my process, like for example, there is a bottleneck in a task in the process, I am going to bring in some people, additional workers into the equation to try to reduce those waiting times. And my question at that point in time is, how many more resources do I need to put into my process so that I can bring my waiting times to a more reasonable level than I have at the moment? So that is what I'm going to be talking about today. And I'm going to introduce a technique for doing this called process simulation. And I'm going to show you how process simulation can be combined with process mining in order to do what I call what-if process mining, meaning trying to analyze not only what has happened, but also what will happen if I make a change to the process. With respect to the outline of the course, we are right in the middle, week 7, and we are going to, and we have gone through all the basic foundations of process mining and the 4 capabilities of process mining: automated discovery, conformance checking, performance mining, variant analysis, and now moving into this topic of simulation and what-if process mining. Business process simulation is arguably the most versatile, widely applicable technique for analyzing a business process quantitatively using numbers. It allows me to analyze the as-is situation if I have modeled it, but it also allows me to analyze the what-if situation. What if I make a change in the process? Or what if I start getting more customers in my process? What will happen? What will be the impact on the cycle times, on the waiting times, on the cost of running the process? The idea of simulation is quite simple. It's like a brute force approach. I'm going to take a BPMN process model of my process, which maybe I have automatically discovered from the event log, and I'm going to enhance it with some so-called simulation parameters. And I'm going to ask a simulation engine to run heaps of instances of this process, say 3 months worth of instances of this process. And when the simulator is running, it will essentially do as if these instances of the process have been created and were running, and it will simulate the fact that a task was allocated to a resource who did the task, and it took him 2 hours, and the next person, she took, let's say, 1 hour. All that, it will keep simulating it in the virtual world of the machine, and it will be recording every single event that it sees during the simulation. And it's going to gather all that data, possibly in the form of an event log, and it's going to allow me to analyze that data and to visualize it using dashboards, animations, or other types of visualizations. Now, how do I simulate a process, or how do I simulate the process, and how do I make sense of what I get back? So I offer you a general view of the process of preparing and executing a simulation of a business process. The first thing you need somehow is a model of your business process. typically a BPMN process model. And we have seen that such BPMN process models can be automatically discovered from the event log. But more classically, you will have business analysts drawing the model, possibly starting from an automatically discovered one and modifying it by interviewing people, by looking at how people do work, by looking at documentation. They just put together a nice looking BPMN model. And our starting point in this course is going to be that we have that model somehow, and we are going to enhance it in order to simulate it. So the second step, which is the one I will focus on today, is how to define a simulation scenario by taking a process model as a starting point and adding information on top of it. So I'm going to explain to you what are the components of such a simulation model. And finally, once we have the model enhanced with the simulation scenario, we are going to run the simulation. We are going to analyze the simulation outputs, and then we are going to repeat these for alternative scenarios. So in other words, I'm going to ask the simulator, please run me 2,000 instances of this process. Give me back the data. I'm going to analyze it using all the tools available in the process mining sphere. And I'm going to then go back to the simulation scenario, and I'm going to simulate different changes. I'm going to look like, what if I increase the number of resources in a task? What will happen if I add one more worker to a task? Or what will happen if 3 of my workers are not available because of COVID symptoms next week? So I will be able to simulate that, to change the simulation scenario, and to run the simulation again, and to analyze the results, and to compare multiple alternative scenarios. So let me start with a process model. And I'm going to work today on a simplified process model of a credit application process at a bank. So this is a simplified process which starts when I receive, say here I receive maybe by an online interface, I receive a credit application, a loan application from a customer. What happens is that someone in the bank, we call that a clerk, will go and check the credit history of this customer. No, so we'll run some searches for previous histories, for previous credits, and look at, has this person always paid on time? Has it been delayed? How many times it has been delayed, etc. What type of loans this person has had or currently has. And based on that and some tools that this clerk has available, we're going to produce some report, including a so-called credit worthiness score or credit score. Then in parallel, somebody else, maybe the same clerk, maybe another clerk, will check the sources of income of this person. So it will go and look at the data that that person put in the loan application, maybe send some emails to the employers to verify that this person is indeed working, or verifying their account statements if indeed this person is receiving a salary on a monthly basis. Based on the data that is collected from these 2 tasks, and once both tasks have finished, so I have a synchronization point here, I will then have someone called a credit officer assess the application. So sometimes this is one person, sometimes it is a team of persons. So they look at all the data, and they look at certain criteria they have, and they fill in some checklists, and then they decide, are we going to grant the loan to this person, or are we going to deny the loan application? If they grant it, then the credit officer will formulate an offer for that customer. Like, for example, yes, we give you the loan. It's going to be a 3-year loan. Your monthly repayment is going to be X. Your interest rate is going to be Y. But sometimes, because of lack of information, or because the credit history was unconvincing, then the customer is notified rejection. Sometimes the rejection gives an option to the customer to send back a response. When the customer does that, then the application will be re-evaluated. But sometimes there is no option and the customer does not send back any information, and then in that case we finish the application. So this is, just wanted to walk you through this process because it's going to be important, as I'm going to be using it throughout this lecture to give you examples of how the simulation parameters need to be defined on top of this process model. Now, to run a simulation, you need to specify 5 things, 5 components, 5 different pieces of information. So let me start by, I'm going to be going 1, 2, 3, 4, 5 from now on. Let me start with the first information you need for a simulator to run the simulation. The simulator needs to know what is the time between the moment a task is enabled, is ready to be executed, and the time, and someone starts executing and the time it finishes. That time is called the processing time, but some people call it activity duration. So for example, take the task check credit history. So if you look and observe a person who checks the credit history and you time it with a chronometer between the moment they start checking the credit history of an application and the moment they finish, let's say that was 10 minutes. So that is the processing time. In very rare cases, the processing time is a fixed value. Of course, people are not robots and different loan applications are different. So credit history check for one loan application took 10 minutes. For the next one, it will take 11 minutes. And for the following one, 9 minutes. And next one, maybe 14 minutes. And the following one, 5 minutes. So obviously, we cannot say that it has a single value. The processing time has a probability distribution is a probability distribution over time. So what we are going to do is that we're going to try to model the processing time of a task by means of a probability distribution. And in this respect, there is a zoology of probability distributions out there. And I'm not going to enter into all of them because this is not a course about statistics and I don't want to start discussing beta and gamma probability distributions. I'm going to limit this course to working with 3 possible distributions. The first one is the trivial one, the constant fixed value. So all the loan applications take 10 minutes. Clearly, that is not the case. It only applies maybe for some automatically executed tasks because those ones are performed by a machine and they always take more or less the same duration. So I could model those ones with a fixed distribution, but any task that is performed by a person will rarely be of a fixed amount of time. There will always be some variability. When it comes to tasks performed by a person, there are usually 2 types of probability distributions out there that are very useful, that are commonly fit the bill, let's say. The normal distribution and the so-called exponential distribution. A task follows, the processing time of a task follows a normal distribution if that task has a certain mean execution time, say 10 minutes, and the deviations in execution times for different instances of this task are symmetrically distributed on the left and on the right of that mean. For example, it takes 10 minutes, but sometimes it takes 8, but other times it takes 12, and other times it takes 7, but other times it takes 13. And these 2 sides are more or less balanced, and the magnitude on both sides, the magnitude of deviations on both sides is symmetric. Oh, sorry. I hope it's not COVID. So we have this average execution time. In a normal distribution, we have a mean and we have a standard deviation, which is a measure of the spread of the numbers around the mean. Very typically, repetitive activities or we call them clerical activities that require following like a very well-defined procedural checklist can be modeled using a normal distribution. For example, if I had a task called check completeness of an application, where I take the application and I go through a checklist to see if everything is in order, that is a task that would normally follow a normal distribution with a certain deviation around it that I will have to specify. You might ask me, oh, how do I get the standard deviation in a distribution? Well, usually what you do to simulate is that you gather some data. Could be coming from an event log. So you gather data from the event log and you look at the mean and at the activity duration, at the distribution around it. Or you can take all the processing times you have observed, maybe through manual observation, just observing people working and taking notes in a notebook, or from an event log, and you will put those values of processing times that you have observed, you put them into a statistical tool that performs a so-called normality test. So you put a bunch of numbers and you ask the tool, tell me if these numbers follow a normal distribution. And the tool will tell you yes or no with a certain degree of confidence, and it will give you the mean and the standard deviation that best fits the data that it observes. Of course, if I have a process mining tool, I will grab those numbers from the tool because the tool produces them for me. The second type of distribution that we normally use in the field of business process simulation is the exponential distribution. The exponential distribution is a bit of a special beast. It models long-tail behavior. So imagine, for example, that assessing an application takes on average, say, 1 hour. That's the average. What does that mean? It means that oftentimes it takes 1 hour or less. You know, in fact, most of the time it takes less than an hour, maybe 30 minutes, maybe 40 minutes, maybe an hour. Sometimes it takes between 1 and 2 hours. Yeah, a few of them take between 1 and 2 hours. And here's the trick of the exponential distribution. Some applications will take, say, 3 hours to be assessed, and a few of them 4 hours and 5 hours. So there are a handful of cases that take a very long time for this task to be executed. If that is the case, then most likely I am confronted with an exponential distribution. The exponential distribution is such that most of the values are before the mean and especially around the mean, and then a few values follow a long tail, and you can see some very, very long values there. Assess activities that are usually modeled or best modeled using an exponential distribution are those that require a detailed analysis of something or decision making. When you have a decision making activity and you have to do some background checks and research, that will take you a potentially exponential amount of time. You know, sometimes it takes you just 1 hour. It's a simple case. Sometimes it takes you a lot. Consider, for example, the process of diagnosing a patient at a hospital or at a clinic. It generally takes the doctor about 20 minutes to diagnose somebody. You know, asks a few questions, takes some measurements here and there, temperature measurement. You know, looks quickly at the history of the patient and say, you have a flu, or you have an infection of this type, or a stomach flu, etc. So usually it takes between 10 and 20 minutes to do it, sometimes around 25 minutes. The average is 20. But sometimes you have these special patients with special types of diseases, very rare diseases, and then to diagnose those ones, the doctor might spend, after you left the consultation room, maybe half an hour doing some research to look at those symptoms that you have and try to match them with some rare disease. So for some patients, the diagnosis takes 1 hour or 2 hours to be reached, for the doctor to reach that decision. So that task, diagnosing a patient in a patient treatment process, will probably follow an exponential distribution as far as the processing time is concerned. Of course, the way you will check if something follows an exponential distribution is to take a few measurements, say 100 measurements, and then put it into a statistical tool and check if it follows an exponential distribution. If it follows, it gives you some parameters that allow you to assess how closely it follows, and then it gives you the mean. And what's funny about the exponential distribution is that you only need to know the mean, and you have already the full, all the distribution of data points can be modeled out of the mean through a certain equation. So let me go back to my running example. Check credit history and check income sources are clerical tasks. You know, there's a certain checklist you have to do. There's a certain number of things you have to do. It's very repetitive. So this is likely to be a normal distribution. Let me imagine I take the data points and I find that the mean is 10 minutes and the standard deviation is 2 minutes. And same thing, check income sources. I take the data, I check for normality. Yes, it follows a normal distribution with a mean of 20 minutes of processing time and a standard deviation of 4 minutes. Assess application. This is something that requires some diagnosis, some assessment, some decision making. There will be a lot of cases here that will take maybe less than 20 minutes or around 20 minutes, but some applications are very special. Maybe it's someone who is running their own business, like a sole trader. And sole traders have very irregular income. And maybe someone who has had some difficulties repaying some loans in the past, but that since then has been, very stable. So that kind of applications will require a lot of discussions among the credit officers. So those cases might take 1 hour or 2 hours. So most cases takes around 20 minutes or less, and some take 1 hour or 2. So most likely I can model that via an exponential distribution. Then make credit offer is a very straightforward task where you have to just put together the data to send the credit offer to the customer. That follows a normal distribution, say with 10 minutes of mean and 2 minutes of standard deviation. Notify rejection similarly, and receive customer feedback is a task that is performed automatically. The system receives a message back from the customer, and the system archives the message so that the credit officers have access to it. That we can say is performed automatically, and it takes 0 time, at least compared to the other ones that takes 10 to 20 minutes. We can model this as being a task that follows a fixed distribution with 0 minutes of processing time. So I have modeled the first thing I have to model in a simulation scenario, which is the processing time of every activity in the process. Having done that, the next 2 things I need are the number 2, the conditional branching probabilities, which is the probability that I take one path or another in a decision point of my process, and the arrival rate into my process, which captures how many instances, how often instances of the process are created. Let me explain these ones with the example directly. So here, imagine that you are a simulator and you want to simulate this process. You will say, let me start this task and this task. Say this task takes 10 minutes. This task takes about 20 minutes. Once I have these 2 tokens here, I put a token here. This is an XOR join gateway, which means that the token will pass through to the output point. So then I assess the application, and let me assume this takes about 25 minutes. Then I jump here, and then as a simulator here, I have a bit of a problem. Oh, should the next task be make credit officer, make credit offer, or should the next task be notify rejection? So for the simulator to be able to, determine what to do next, what the trick that we play is that we give as input the branching probabilities, the probability that each flow coming out of a decision gateway will be taken. So I can give, let's say, by previous observation, I have found that 30% of applications are accepted, and therefore we make a credit offer, and 70% of applications are rejected, and therefore we notify rejection to the customer. So the branching probabilities coming out of this gateway will be 0.3 and 0.7 respectively. Then I do this task, then I do this task, and then here I have a choice again. Should I repeat or should I finish? And for that, I need the user to specify to me the branching probabilities. Say this one is 0.3, and consequently, this one will be 0.7 because the probabilities coming out of the decision gateway need to add up to 1. So if one is 0.3 and there is another one, then the other one should have 0.7. So let me assume that those are the branching probabilities. Now, the simulator needs to do something. It needs to figure out how often should we create new instances of the process. Should we create one instance every 20 minutes or every 30 minutes or every half an hour? Sorry, or every 1 hour. So for that, I need to specify to the simulator the arrival rate, or more specifically, the inter-arrival time. Let me explain. Imagine that you have 200 applications, 160 applications per day, meaning new loan applications coming into your bank. That means that you are receiving 20 applications per hour. Or if you are receiving 8 applications per day, 16 applications per day, and the day, your working day has 8 hours, that means that you are receiving 2 applications per hour. Now, what you need to tell to the simulator is not how many applications you receive per hour, it's how often on average do you receive an application. And this is done by, this is called the inter-arrival time, and it's basically 1 divided by the arrival rate, which we call lambda in the jargon. So 1 divided by the arrival rate within lambda, that is the inter-arrival time. So if I receive 16 applications per day on average, and my working day has 8 hours, it means that I receive 1 application every half an hour. And this is the number you need to give to the simulator, because the simulator will then start, on average, creating 1 application every 30 minutes. Obviously, applications will not arrive exactly every 30 minutes. Sometimes the time between one loan application arriving and the next one is 1 hour. Sometimes it is 15 minutes. Sometimes it is 10 minutes. So I need to also tell the simulator the probability distribution of the inter-arrival times. And how do I do that? Well, usually in most business processes where customers arrive whenever they want, the inter-arrival times follows an exponential distribution, the same type of distribution that we were using just a minute ago for the processing times of tasks that involve decision making. And why that happens? Well, it is because things happen in bursts. You know, there are a lot of applications that arrive one after another, for example, on Monday morning. And then, you know, Thursday is a very calm day, so there are very few applications that arrive on Thursday. So there are times where lots of applications, the inter-arrival rate is very small, things arrive in a rush, and sometimes the inter-arrival times are very long, very spaced. And that exactly that type of behavior can be modeled with a exponential distribution. In the statistics jargon, we say that the arrival of cases follows a Poisson distribution, as someone wrote in the chat window in Zoom just now. So, and this is a very common type of arrival process. In fact, one of the cases where it is not true is if the customers arrive via bookings. If you have a booking system and customers have to pre-book, for example, in a dentistry, then indeed the arrival rates will not follow an exponential distribution. They will follow rather a normal distribution, because the booking system will force people to come at regular intervals plus minus a few minutes. But unless there is a booking system in place that prevents people from creating instances of the process, of your process at any time, most likely your arrival rates in your process, your case creation process, will be a Poisson process, and the inter-arrival times will be following an exponential distribution. The fourth thing, so we are going very quick now, so please ask more questions. The fourth thing we need to specify to simulate the process is how many people are there to perform each task in the process. Because of course, if I have 10 people available to perform a task, the waiting times of that task are going to be slower than if I only have 2 people to do it. So I need to specify that. How do I do it? Well, I define something called resource pools. So it's like I identify the roles in the process. For example, in this loan application process, there is clearly a clerk, one or more clerks, and one or more credit officers. So I will say that the clerk is a resource pool, and there are many such clerks. And I will say that the credit officer is a resource pool, and there are many such credit officers. And for each of those types of resources, we call them resource pools, I'm going to specify their name. I'm going to specify their calendar. When are they available? Because normally people in the real life are not available 24/7. They work during certain times of the day, during certain days. So I have to attach a calendar to every resource pool. And optionally, I can give a cost per hour of one resource of that pool. For example, people in this pool cost on average 25 euros per hour. And I have to do the same for each pool. So let's imagine there's a second pool in this process called the credit officer. This is the cost of the hour of a credit officer, 35 euros per hour. And the credit officer works from 9 to 4 on Monday to Friday. Note, the working times of the clerks is not the same time as those of the credit officer. Plus, I also need to know how many clerks there are, let's say 2, and how many credit officers there are, let's say 1. So I forgot to write in this slide that you also, of course, need to know the size of the resource pool, how many clerks there are, how many credit officers there are. And finally, I need to specify to the simulator a mapping between the task in the process and a resource. So every task in the process or activity, say T, every task in the process, I should map it to a resource pool. Concretely, let me say that the check credit history task is performed by the pool called clerk. Check income sources is also performed by the clerk. Know that the two are performed in parallel by the same resource pool. That is not a problem. So it might mean that one clerk does this and another clerk does that, or it might be that the same clerk does this one and that one sequentially. It doesn't matter. The credit officer handles the task assess application, make credit history, and also notify rejection. And receive customer feedback is an automated task. Therefore, I will assign it to a special resource pool that I will call the system. And this resource pool is not going to play a role, any significant role in the simulation, because the tasks that the system performs are instantaneous. And therefore, they do not affect the cycle times, nor the waiting times, nor anything. So I put it there for completeness. I say this task is performed by the system, but it's pretty relevant because this task, anyway, we said before, takes no time, 0 minutes. Once I have specified these 5 pieces of information on top of a process model, I am ready to run a simulation. So, and the simulation is then going to return me some simulation outputs. Now, when you combine simulation with process mining, so when you do simulation and process mining, something very interesting happens. The simulator generates a simulation log. It's exactly the same type as event logs that we have seen coming from different types of data sources. But this log that the simulator will generate with a bunch of task case executions and task executions assigned to different resources, that simulation will be done that log is completely simulated. It's not the result of real stuff, it's the result of random number generation according to the parameters that I have defined. Notwithstanding that, it is a log, and I can use any process mining technique to analyze it. I can automatically discover a process model out of a simulation log, enhance it with performance characteristics. I can animate the process model against that event log, and I can derive a bunch of dashboards. To make it concrete, let me then move to a demo in a Promore. So let me discard, and let me bring a Promore with the server we are using for this course. And I have loaded into my Promore workspace the same credit application process that I used as a running example in this lecture. So I will double click on it and open it in the Promore editor. So this is the process model we saw: check credit history, check income sources, etc. And I can click here on the left-hand side to open the simulation drawer, which contain where you can enter optionally on top of a process model a bunch of simulation parameters. I can now click on a task, and in the simulation parameters, I will see the parameters of the task. I have already pre-populated this model with the parameters that I presented during the lecture. This task is performed, check credit history is performed by a clerk that I have defined elsewhere called a pool that I have defined elsewhere called the clerk. It follows a normal distribution with a certain mean and a certain standard deviation in minutes, which is the one that I presented just a minute ago. I can click on check income sources and then enter the simulation parameters. The same for assess application. Oh, by the way, assess application should not be with the clerk, it should be with the credit officer. Make credit offer should be with the credit officer, and notifies rejection should also be with the credit officer. And receive customer feedback is assigned to the system, and it has an execution time of 0 seconds. Note that assess application has an execution time that follows an exponential distribution because it is a decision-making task, and most likely this is a better way of modeling. I'm saying most likely because, of course, all the decisions I made here, I should try to validate them using some statistical testing. Fantastic. So once I have done that, if I click anywhere in the canvas, I will get all the simulation parameters divided by tabs. So the tasks have already been entered. The general tab tells me the arrival of cases. So I'm going to say that in this process, the arrival of cases follows an exponential distribution with an inter-arrival time. Let me make it of 20 minutes. What does an inter-arrival time of 20 minutes means? It means that I receive 3 loan applications per hour on average, which means that in one day I receive 24 loan applications in one working day. I say that this is 20 minutes. Here I can choose how many instances of the process I am modeling. I'm going to simulate 2,000 process instances. How do I know if this 2,000 is a good number? Well, 2,000 instances which arrive every 20 minutes gives me about 40,000 minutes of simulation. With, let's say that in one day I have well, let me divide this by 60 to make it hours. So I'm simulating 666 working hours. One day has 8 hours. So I'm modeling, I'm going to simulate 83 days worth of cases using this. That's about 2.5 months, which is kind of a reasonable time frame. I could maybe double this and make it 4,000 instead of 2,000 to simulate 166 days, which will be even like almost 6 months, which is a nice time frame to draw conclusions from. So to determine how many instances of the process you need, well, come up with a number, multiply times the mean inter-arrival time, and convert it back to working hours, importantly, not to calendar hours, but to working hours, and get an idea of how many days of work that represents. And usually you want to simulate, you know, a period of like 2 to 6 months, or maybe up to a year worth of executions of your process. Then there is a resources tab where you can specify resources, and here clicking on plus means I can add more resources. I have already specified a clerk resource. I call it clerk. Here is the cost per hours, and here's the number of clerks I have, 4. I have specified one called credit officer, 4 resource of credit officers, 50 per hour, etc. Each of them follows a certain timetable, and there is a separate tab where I can specify my timetables. There are 2 predefined timetables. One is called the arrival timetable, usually defined as Monday to Friday, 9 to 6, but you can change it. And there is a 24/7 timetable, which means every day, 7 days a week, 24 hours per day. The timetables are here. I can click on a timetable, and I can add time slots to the timetable. So I could even specify that my working times on Monday is like 9 to 12, on Tuesday is from 9 to 16, etc. So I can specify relatively complex calendars where a calendar, a timetable consists of one or many time slots, and every time slot is a day of the week or multiple days of the week, a start of the day and an end of the day. So in that way, if you think about it, you can specify relatively complex calendars on a weekly basis. These calendars are then assigned to resources. For example, the clerk follows the arrival timetable, and the credit officers does the same. And finally, for every gateway, of course, I need to specify the branching probabilities. So here I'm saying that in this gateway, 20% of the times I go to notify rejection, and 80% of the time I go to make credit offer. Okay. So if any simulation parameters are missing, the tool will tell me which one. If not, I can save the model, and it goes into my workspace, and I save the model with the simulation parameters inside. Then in the portal, I take my model, I select it, and I can go to Analyze, Simulate Model, and this is gonna run a simulation using the parameters that I enter, and it's gonna return me a log. So let me call this log Scenario 1. The log will be appended to the current directory, and now I can select the log and I can analyze it, for example, using the performance dashboard. So Apromore will now compute all the statistics of this simulation. For example, the case duration, which is what we, in scientific terms, we call the cycle time, which in this case, the average is 3.66 hours. The distribution of the case duration in calendar time, the distribution of the case duration in timetable time with respect to the arrival timetable that I defined in the simulation model, because note that 10 hours in calendar times means one thing, you know, for example, from 1 p.m. to 11 p.m., that's 10 hours, whereas in timetable time, 10 hours or 10 working hours means a different thing. For example, from 2 p.m. to noon of the next day, there are only 8 hours. It's 2 p.m. to 6 p.m. of this day and 8 a.m. to noon of tomorrow. So working hours or timetable hours is not the same as calendar hours. And here I get calendar hours, and here I get working hours. It also calculates costs, waiting times in calendar time, and resource utilizations. Here, the resource utilizations are fairly low. Okay, so I can go back to the editor, and I can now play a new scenario. Let me imagine that now, instead of receiving 20 applications, no, one application every 20 minutes, I start to receive one application every 10 minutes, which means the number of loan applications doubled. I'm receiving it twice more often. So I'm gonna save this with the same name or with a different name. I'm gonna allow myself to reuse the same file. So I just overwrote the previous file. And I'm gonna pick it again and analyze, simulate. And again, the simulator will run. And I'm gonna save this as scenario 2. Scenario 2, save, guys. So, so that's gonna save a second log in my workspace, which I can again view in the dashboard. And what do I see? Now the average time is almost 5 hours. If I recall that when the applications arrived every 20 minutes, it was 4 hours or 3.6 hours. And now that the number of applications doubled, the cycle time of my process has gone from 3.5 hours to 4.9 hours. So now I can see the effect that a higher intensity of arrival has had on this process. Here is not too bad because the resource utilizations were very low, but here I'm getting to the limit. So I foresee that if I run a third simulation scenario and now I double again the arrival rates, these waiting times are going to explode because my system becomes busier because there are more and more applications arriving more often, and therefore the resource utilizations are going to get close to 100%. And when resource utilizations jump above 100%, my times are going to increase tremendously. So I'm going to save this here, and I'm going to now pick the credit application simulation and do analyze, view, perform, simulate, analyze, simulate, and I'm going to create a third scenario. This time with a very, very high workload. I'm going to call this very high workload. So I have here my very high workload, and I can open a dashboard for it. And it's going to show me that the average cycle time now is 1.17 weeks. No surprise. Because if I scroll down, I will see that the resource utilizations are 100%, which means this system is not stable. A resource utilization of 100% or close to 100% means that waiting time will keep increasing forever unless I bring in more work or unless I stop discarding some of these loan applications that are arriving in some way, for example, by eliminating some of them that do not fulfill the requirements. Okay, so, and by the way, I can also do anything I can do with the process mining tool using these simulated logs. Let me take, for example, the credit application process model and two scenarios, scenario 1 and scenario 2, which I simulated before. You can select all three files and go to animate, and it's gonna create a log animation of the two logs against the process model, where in this case, the blue tokens are the simulation scenario 1 and the red tokens are simulation scenario 2. And that way, I'm going to see a little bit of the token build up in this process as in a simulated way. So I can see that, you know, somewhere here, I will see that there is a bit of a build up of red cases here, you know, that need to be eaten by the assess application task. And I can see effectively that blue tokens are going faster than the red tokens, although not by much. If I decrease the arrival time, I will see that, you know, the blue tokens are overtaking the red tokens very quickly. In here, what I can see is that the two scenarios have more or less the same behavior, really. So I'm very reassured it's something we can do. You might wonder, why are things coming in batch here? This is because my process is running per day and on a circadian basis. So lots of applications arrive on Monday morning and need to be eaten through the week. That's why at the beginning of the week, there is a lot of build up here at the start. And as the week progresses, I see tokens flowing through. The new tokens of the next week are already coming here. Yeah. I can even see in the animation this cyclical behavior in my process. Okay, and you can also grab two scenarios, two logs, and go to dashboard and do a multi-log view, or I can double click on one of these simulated logs and open the process discovery and go to the duration overview. It's a log. I can analyze it in any way. I can even compare the log of the as-is process with the log of a what-if process that I have simulated. Okay, so simulation is a pretty powerful tool. It's also a pretty dangerous tool. There are a few pitfalls that you have to be aware of in simulation. First thing, you need to remember that a simulator works by drawing random numbers. And you know how random numbers work. If you run multiple times a random number generator, you get multiple numbers. That's the nature of it. So unless you kind of take both times the same seed, but of course the simulator to make it really, really random, you know, does not reset the seed. It just keeps generating random numbers. So if I run the same simulation that I show you twice, the same scenario, I will get slightly different results. If the differences are not too large, that's okay, but sometimes the differences are too large. In that case, one way to tackle that problem is by making the number of instances that you simulate larger. So instead of simulating 2,000 instances, try simulating 4,000. Or the second approach to even out difference between runs is to make multiple runs and to do an average. Whatever you conclude, you do it with respect to a mean of multiple simulations. And if you are brave enough, you can even compute confidence intervals over multiple simulations. Okay, this is not too bad, but bear in mind that process simulation can also give very approximate results because of some simplifying assumptions that it makes. I list here 4 simplifying assumptions that simulation makes. It assumes that all the cases are following the process model that you simulated, which might not be the case because your process model might not capture every possible deviation. It assumes that every resource works on only one task at a time, that there is no multitasking. It assumes that if a resource becomes available and a work item is enabled at that point in time, that the resource will eagerly grab the work item and start working on it. In other words, a simulator makes an assumption of so-called robotic behavior. People have tasks, and when they are available, they pick a task, they do it, they become available again, they pick the next task, they do it, they pick the next task, they do it. In a manufacturing process, this is kind of more or less the behavior you will observe. But in a service delivery process, people tend to batch multiple cases in a single go. They tend to be distracted by other work they have somewhere or checking their Facebook. Sometimes they feel a bit tired and they don't feel like assessing a new loan application. I'm completely like overloaded. Sometimes they go out for a coffee break. So of course, the simulation results are not going to be 100% accurate because of these effects. So one of the things you need to do is to verify that the output of your simulation. So if you take the as-is process model and you enhance it with the simulation parameters of the as-is process, of the existing process, and you run a simulation, you need to check that the outputs that it generates in the as-is scenario are similar to what you observe in practice. For example, that the cycle times of your simulation model are similar to those that you observe in your existing process. If not, that means that your simulation should not be trusted. Well, assuming that the effects of these different parameters, different exogenous factors are even out and that your simulation is relatively close to reality, a third problem of simulation is data quality. So, like many other things, simulation is garbage in, garbage out. If you give to the simulator just guesstimates of how much processing time every activity takes, or if you do not really validate the numbers that you're putting to the simulator, of course, the output that it will give you will not be very accurate. Real-life processes are very complex, and therefore modeling them in all the glory of their details is sometimes not a humanly possible task. So one way to cater for these limitations of data quality is to take a large amount of data, say an event log of your last 6 weeks, and to build a simulation model using process mining techniques. You take your event log of, say, 6 months of data, you discover a BPMN process model out of it with a certain level of details, and you start filling the parameters based on the data. So how much time this task takes, you look at the data in the event log and you fill it in. How often do a new case get created? Look at the data in your event log and fit the data in. Okay, doing this is very, very tedious. So in our research group at the University of Tartu, we have a long-standing project of trying to build a machine, a software that takes as input an event log and produces as output a process model with all the simulation parameters tuned in such a way that that simulation model produces logs that are very, very similar to the real log. So what we try is to build a simulation model out of the data that produces simulated logs that are as similar as possible to the original log. That machine is called a Cmod. What the Cmod tool does is that it first takes the event log and it discovers a BPMN model in the first step, using the same algorithm that a promoter uses, which is called the split miner. It then replaces the log against the model in order to make sure that all the traces are following the model, because remember, one of the assumptions the simulation makes is that the traces follow the model that you're simulating. So to compute all the statistics, a promoter needs to repair a little bit the log so that it follows the model that it discovered. And then it extracts all sorts of parameters, the inter-arrival rates and their distribution, the activity durations and their distribution, their branching probability, etc. And it assembles them into a simulation model, and then it runs BIMP to simulate it. Every one of these items in here requires Cmod to make some choices about how to model the task, the activity distributions, what distribution to use, how to model the inter-arrival times, how many resources to put, and how many resource pools to have, etc. There are a lot of parameters that Cmod is considering when doing this, and depending on how these parameters are set, I will get different simulation models. So what Cmod is doing is that it takes every simulation model, it makes it generate one or more log, it compares it against the real life log, the ground truth, and it computes a loss function. In this case, it's a distance metric. And it uses a so-called hyperparameter optimizer, specifically a Bayesian optimizer, which tries to navigate through the space of different configurations of these parameters in order to produce, over many iterations, an event log that resembles, a simulation model that produces logs that are very similar to the ground truth. And once it has reached some convergence, it is happy and it gives you a simulation model with, let's say, a good level of similarity with respect to the event log. Of course, it's never perfect. Maybe you are happy if you get a simulator that is simulation model that is about 60 to 70% capable of reproducing your original log, but it's really to make estimates. So in practice, this can be quite useful already. Okay, so that's it for today.